Yes. Okay. The case of the Mr. Yang, you should have given us homework on Friday. We should have given us homework on Friday. Can we do Tuesday? Give me 2 days of Tuesday.
Okay, all right, you guys got your quizzes back. I do want to talk about. I think the most important thing from the quiz that's going to carry over. Well, the Riemann sums table of values. I think you're going to see that quite a bit, and I think most of us did very well. You know, being able to hold the width and height and all that. The second is power rule. So power rule is very important. You're going to use it for the rest of the semester. And it's kind of like your foundation for all your integral problems. So today we're going to talk about U substitution, which is for more complex problems. But power rule is going to be always your first option. Okay, you always want to explore the possibility of power rule. If power rule doesn't work, if it's too complicated for power rule, or it's impossible because of order of operation issues, then you explore your second option, which we're going to talk about today. But this type of problem, I want to kind of point out all the different mistakes that I saw so that we can make sure that we don't repeat them in the future. So the first thing is, especially if there's only one term in the denominator, which we know we can split up and we go through all the steps of putting together and getting ready for power rule. We can't do this. We can't treat numerator and denominator as separate things and just do power rule for the top and bottom and leave it like this. Okay, so we have to resolve that 3x to the 1/2 somehow with the numerator before we can do power rule. I know this feels easier to do just to separate everything and do power rule, but this is not correct. Okay, so that 3x to the 1/2 is not separate from the numerator. We can't just do power rule below and above. Okay, so that's one thing I want to point out. Second thing is when you bring that denominator up, first the variable needs to be brought up as a negative exponent. Okay, and second, this 3, if you want to bring that 3 up to the top, it's not a 3 up top. It's a what? It's a 1/3. Okay, so but this issue here is bringing the numerator denominator up and adding to the numerator term. So I think some students realized you got to bring that 3 up to the top, so they brought it up and they changed it to either a plus or a minus or a multiplication. But that's not quite it as either. Okay, so we are going to bring it up, but we can't bring it up as an addition or subtraction of terms. The third is you bring the numerator denominator up, but then you only multiply with the last term. Okay, so if you bring it up and you want to multiply, that's fine, but it needs to multiply through the entire expression. Okay. Now, the way that I presented it was splitting up into individual fractions first. That way, you're never forgetting that every part of the numerator is also influenced by that denominator. But you can also bring it up to the top and multiply everything through with a parentheses. That's fine as well, but I don't teach it that way because I see a lot of students forgetting to put parentheses and distribute. So I just have you guys split up into individual fractions first to take care of that issue and then bring it up individually. Okay, let's see, a couple more. Okay, here's another issue that I saw. When you bring that denominator up, okay, it comes up as 1/3 x to the negative 1/2 parentheses. But we have to distribute first before we do power rule. Okay, we can't do power rule for this part and power rule for each of these terms because these are being multiplied. Okay, power rule doesn't exist with terms being multiplied. So we have to resolve everything else. If there's a plus or minus between the terms, then we can do power rule, but we can't do power rule here and then power rule for each of the terms individually. So you have to first expand everything out, get all your parentheses to go away, and then you can do power rule. So we got to distribute, multiply your coefficients, add your exponents. Okay. And I saw some students doing something creative, trying to apply quotient rule for antiderivatives. So quotient rule, we don't have quotient rule for antiderivatives. So we can't quite do, integral of f times g minus f integral of g all over g squared. Okay, so that rule doesn't exist for antiderivatives. So we can't do quotient rule for antiderivatives. Okay. However, yeah, the more common mistakes are the smaller ones, and the smaller ones are just what I mentioned before. How if you bring that 3 up, it doesn't come up as a 3, it comes up as a 1/3. You want to bring that 3 up. And then finally, your exponent. I see a lot of students brought the exponents up because they knew this that variable has to come up. But if you move your variable up to the top, your exponent has to change signs. Okay, it doesn't stay as 1/2; it needs to go to -1/2. Okay, so these are the more common mistakes, which I understand. You understand the big picture. It's just that denominator bringing up just caused a little bit of issues, which altered your answers. So those are the biggest things that I saw with these types of problems. I want to point those out. Okay. Okay, so let's go to page 7 in your packet. Okay, so use substitution. Today we're talking about a more involved integral rules. Use substitution is the reverse of derivative chain rule. Okay, so if you think about derivatives from first semester, if f of x equals sine of 3x, what's the derivative of sine of 3x? Cosine of u times u prime, so cosine of 3x times 3, right? So if my derivative is 3 cosine of 3x, which means that if I wanted to find the antiderivative of 3 cosine of 3x, that must bring me back up to what? Sine 3x, right? So if I'm going backwards, I should be able to get back to where I started. So the question is, how do we know that this 3 is going to disappear going backwards? Okay. And so use substitution is going to help give us the structure and an orderly way to keep track of all the moving parts, because usually it's harder to, like in this case, it's harder to put things back together than it is to take things apart. So I want to kind of show you one more involved chain rule, because this doesn't seem like a huge deal, right? Just adapting that 3. But I want you don't have to write this down. I just want to kind of show you for first semester. Remember these more complex chain rule problems from first semester involving trig. So we talked about how, okay, if I want to do chain rule for derivatives, if I see any trig with that exponent out of place, I rewrite it with brackets. Then I understand that there's an outside and inside portion. 4 bracket cubed is outside derivative. Sine of u becomes cosine of u, and then we got to do that u prime. So if we clean all that up, we get a pretty involved derivative, right? So we know chain rule to get from a function to the derivative, but what that also means is if I were to take the antiderivative of this, what should that take me back up to? The original, right? So, but if you look at this problem here, thinking about all that is required to get from here to here, there's a lot of moving parts, right? Like, how do we know that the 12 goes away? How do we know the cosine goes away? And how do we know that there's just a 4 without a 4 in the denominator? But we can think about power rule. We can think about antiderivative for trig. But this feels like a pretty involved, complicated process. Right? Chain rule is easy to take apart, but putting things back together is harder. So we need some help in undoing chain rule. And use substitution is going to provide a structured, methodical way to kind of help with this antiderivative process. So that's the big picture. Okay, undoing chain rule is why we need use substitution. Gives us another variable to kind of help track all these moving parts. Okay, so let me start introducing this process here. I'm going to jump directly to example 2, and then I'm going to kind of refer back to these steps as we go through. Okay. Okay, so first is your parentheses is going to be a very big part of your problem. It's going to help you kind of give some structure. So we do see a set of parentheses already built for us. And so the rule of thumb is, okay, let's start with this here. First option is always power rule, okay? So this is x times x squared plus 1 to the 15th dx. If we always want to think about power rule first, what's the issue that you see with this problem? What's going to be difficult to do? Because if I want to do power rule, what needs to happen with the parentheses? It needs to go away, right? So what would it take for the parentheses to go away? I got to do 15 sets of parentheses and expand all the way out. We don't want to do that, right? That's not efficient. Sometimes you're stuck, either power rule not being able to work because of order operation issues, but other times it's just a convenience issue. We don't want to, I mean, if this is raised to the second power, that's not bad. We can FOIL it out once and distribute the x through, and then we can do power rule. But anything more than 2, we would prefer to apply a different rule. So we always want to remind you, okay, look to see, does power rule apply? If it doesn't, then let's look at more involved options or more complicated options. So now we want to consider U substitution. So we look inside the parentheses, and if we see a value inside the parentheses, that's usually our initial guess. Okay, it is a little bit of guess and check. We always want to pick out the U value, and the point of it is we're going to try to shrink this problem into an easier a problem to solve, and then solve that problem and then bring it back out again. So we want to introduce a variable to allow for this problem to be a little bit easier visually to look at. So we'll let the U value be the portion inside the parentheses. Okay, and it's just the portion inside. Okay, don't include the exponent. This is right now, we're just going to stick with this rule. Always look inside the parentheses. Then we'll look at some problems that may not always be what's inside the parentheses. But at least this is kind of helps us get started. Okay. So the next thing is we're going to find the derivative of U with respect to x. So after you find your U value, you're always doing a du over dx. So that's why we're having to learn derivatives first, because even with integrals, we have to rely on derivative steps. What's the derivative of x squared plus 1? 2x, okay? The 1 goes away, okay? Next step, you're going to solve for dx. Okay, so I'm going to cross multiply until I get dx by itself. If I solve for dx, what do I get? Get du over 2x. Okay, so we've done the preliminary work to make the substitution that we need. So our hope is that after we make substitutions, this will look like an easier problem to solve with a rule that is clearly available, and then we're going to apply that rule. Okay, so I know what I'm going to replace that x squared plus 1 with. Replace it with u. I know I have a replacement for dx, which is d over 2x, and I'll leave that x alone. Okay, so I'm going to just recopy the entire problem, and I'm just going to replace what I underlined in red. But everything else stays. So the x stays, the parentheses gets replaced with u, the 15 stays, the dx gets replaced with du over 2x. Yes, question. say,
Like why you like
uh-huh.
that?
Yeah, because when we do U substitution, that's exactly what we're going to do. We're going to replace all the x's, or try to replace all the x's in terms of u. And I'll show you the purpose why is because we should be able to, we want to create a simpler version of this problem. Right? So if we go through the steps here, hopefully you can see why we do it, but it's going to just give me a couple more steps here. Now, okay, everybody good so far in terms of the steps? Okay, now we can't proceed unless the x's goes away. Okay, do you see a path where the x can go away? Okay. There's x in the numerator, there's x in the denominator. What can I do? Cancel out. Okay, so you know you're on the right path first if your x's goes away. Right? If your x's remain, we can't do a problem where the x's and u's are multiplied and trying to resolve it. Okay. Now this too is important, but we're just going to treat it as a number. So where can I put this number to make it easier for me to separate things? Yeah. Well, I'll keep it in the denominator, but I'm going to push it out as what? As coefficient. So what's the coefficient? 1/2. Okay. Right. 2 in the denominator is same thing as a 1/2 in front. Okay, so if you go through U substitution correctly, you should be staring at an easier looking problem than what you began. Okay, so that needs to be true. Okay, so if you go through U substitution and your problem looks more complicated than what you started with, something or as complicated as what you started with, that means we didn't either go through the same steps or we didn't select the correct U value. So you see that this is an easier looking problem than this one. Okay, so now, if we look at this problem, we should be able to identify the rule that we can use. What rule does this look like that we can use? Power rule, right? Power rule says if I have integral of u to the n du, it's u to the n plus 1 over n plus 1 plus c. That 1/2 just hangs out. Okay, just going to tag along and attach itself to whatever my antiderivative is. Okay, so 1/2 is going to stay. U to the 15th becomes u to the 16 over 16 plus c. Do some more cleanup. I can push this 2 and 16 as what? 32 in the denominator, so I can make it 1 over 32 u to the 16 plus c. Okay, so we have our answer. We found the antiderivative, but what variable do we start with? X. So now we're going to bring our x variable back into our answer. Okay, so our u variable is just a temporary variable to help us visually see this problem in a different light. And then after we finish the problem, then we bring the messy, more complicated variable back. Okay, so replace u back with what? Okay, so replace u with x squared plus 1, right? U is to x squared plus 1. Okay, any questions with that process? We'll do a lot more of these, but yeah.
After you replace the u with the original
variable,
do you have to simplify any further? Or you'll just leave it?
Yeah, you can pretty much leave it. Yeah. I think as we see more problems, maybe I can point out things that that I need you to do, but for the most part, you can leave your answer the way you have it. Okay. Okay, good. Example 3, integral of x squared secant squared 2x cubed. We don't have a rule that can handle this, right? And also want to make sure that we understand that we can't apply integrals separately if there is a multiplication in between. So I can't say, oh, x squared, that's x cubed over 3, and secant squared is tangent, and I'm done. So anytime there's multiplication involved, I have to kind of treat it as one connected thing. I can't think of it as, oh, I can do a power rule here, and some other rule here. We have to resolve it since it's all connected. So first thing we recognize is we don't have a single rule that can handle this problem, right? We do have some trig rules, but the trig rules are not as complicated looking as this, right? There's too many parts here. So that's going to lead us to use substitution as our second option. And if we want to find a u value, where's the first place we look? Inside the parentheses. Okay, so right now we're going to let that be our rule of thumb. As we look at more problems, that may not always be the case, but we're going to kind of at least let that be our starting point. Okay. So go ahead and underline the 2x cubed and go ahead and underline the dx. Okay, because you're always going to replace your parentheses in terms of u, and then eventually the dx has to be replaced as well. Okay, so that's our target. Okay, the x squared, we're hoping that it goes away on its own. Okay, so we're kind of waiting and seeing, but right now our first priority is to replace these. Okay, and the hope is we want to introduce a variable u in hopes that this will turn into an easier problem for us to solve. Because that's the whole purpose. Can we turn into an easier problem? And once we get into an easier problem, can we find a rule that matches that easier problem? Okay, so u value is 2x cubed just inside the parentheses. All right, and then as soon as we find u, we always find the derivative. So we always do du dx. That just means I want to find the derivative of u with respect to my independent variable x. Okay, 2x cubed becomes 6x squared. Right. Cross multiply. Okay, solve for dx. Okay, solve for dx. Dx equals du over 6x squared. And you're just going to substitute what I had underlined in red. I know there's still this x squared sitting out here, but we're just going to we're kind of waiting and seeing if that will go away on its own. Okay. All right. Can we see all the x's going away? Yes, because x squared is in the numerator and x squared is in the denominator, right? So good. That's a good sign that we are going along the right path. What can we push out in front? That's not part of the integral rule. 1/6. Good. So we always want to kind of separate. I mean, we want to keep track of our coefficient, but we don't want it to let it get in the way of helping us seeing what rule we want to use. Okay. Compare. Are we looking at an easier problem? Yes. Okay. So if you go through your substitution correctly, you should always be staring at an easier looking problem than what you began with. Okay. If it looks the same or if it looks more complicated, something else didn't go quite right. Okay. Now, do we have a rule for secant squared? Yeah. What's the integral of secant squared? You have it. Remember, tangent's derivative is secant squared, so secant's antiderivative is tangent u, right? Okay, so we know that secant squared turns into tangent u plus c. Okay. We pretty much are staring at the answer. What's the last step? Yeah, replacing u back in terms of x. I see a lot of students do this where they get to this answer and they leave it alone, and just make sure you bring it back to x. I mean, this is a minor issue. I'm not taking a lot of points off for this, but just remember, if you go through your substitution, it's only a temporary variable. You want to bring your original variable back into your final answer. Okay, example 4. our first option is always looking, can we expand? Can we just rely on power rule? What's the issue with trying to rely on power rule? Can I distribute this x cubed through? Okay, so the order of operation kind of prevents us, right? We can't distribute the x cubed through until the square root is resolved. The square root is not going to be resolved because we can't, there's no like terms inside. So this is kind of stuck in this form. We can't distribute through. We can't use power rule. So the first step is assign the u value to what's inside the parentheses. So if you don't see parentheses, can we rewrite the problem where we do see parentheses? 5 minus x to the fourth raised to the 1/2. Good. All right, so there we have it. Underline what's inside the parentheses, underline dx. Those are your first priorities, trying to get those pieces to be in terms of u and du. Okay, so u value equals okay, du dx. Oh, and keep remembering, keep reminding yourself that your exponent is not part of your u value. Okay, all right, good. So du dx. 5 goes to 0. Negative x to the fourth becomes negative 4x cubed. Okay, good. Cross multiply. Solve for dx. Dx equals right. Dx is du over negative 4x cubed. All right. Make our substitutions. Replace the parentheses with u, but we don't want to forget it's u to what power? 1/2, right? So even though that 1/2 is not part of your u value, we don't want to lose that 1/2, right? That 1/2 is still going to be part of our problem eventually. Okay, times du over negative 4x cubed. All right. We can't proceed unless the x's go away. Do the x's go away? Yes, goes away cleanly, right? Okay. What can we push out in front? Negative 1/4. Okay. Are we looking at an easier problem than what we started with? Yes. Okay. So that's an important part of the process, right? Because the whole purpose is you want to solve an easier problem. If you're not staring at an easier problem, then something didn't go quite right, right? It kind of it's not serving its purpose if we're not solving an easier problem. Okay, so this is a straightforward power rule, right? Add 1 to the exponent divided by that exponent. So what is our new exponent? Yep, 3 over 2 divided by 3 over 2 plus c. Okay, that 3/2 is in the denominator. I can flip that 3/2 to the top as what? 2/3. I can clean that coefficient up as what does this become? Yeah, negative 2/12, which reduced to be negative 1/6. And then what can I replace u back with? Yeah, 5 minus x to the 4. Yeah. Okay, any questions so far? Now we see with these 3 examples how after you substitution, all the x's just kind of goes away cleanly, very nicely for us. What is it about the u value that allows that to happen so cleanly? And can we predict that that the x's will go away before we get there. Okay, what are some clues that kind of helps you see, wait, if I see this u value and this remaining x, I know I can, I'm gonna have a good chance of canceling out. What do you notice about the u value versus the variable that needs to be degrees, right? Degrees are always what? One higher, right? And that's a good indication because you know that if your degree is one higher, the derivative will be 1 degree lower, and that's going to nicely cancel out. It doesn't always work out that way, but that's a quick way for you to kind of, okay, to kind of visually see, okay, I'm probably along the right path because I'm picking my u value, which is 1 degree higher, which will take care of that remaining x's that is 1 degree lower. Okay, so that's so you see how degree 3 versus degree 2, that's a good indication. Degree 4 versus degree 3, that's a good indication. Okay. All right. Good. Let's go to the next page. Okay, so sometimes problems are not as clean as these. So I want to talk through some of this. Okay, first thing we recognize with example 5 is that we don't have a rule that can handle this mess, right? We don't have a rule that's specifically tangent to the 5th times secant squared. So we're kind of stuck not really having a trig to pick from. But maybe we can create some parentheses to kind of help us along the way. So maybe use substitution after we see some parentheses as possible. How can I rewrite these using parentheses? Where can I put that 5? Where can I put that 2? Tangent x to the 5th and secant x to the 2nd, right? We can force those exponents outside a set of parentheses. So if we see 2 sets of parentheses, what do? How do we know which one is the u value? We can kind of do a quick check, right? Kind of see, wait, which one is going to be a better fit, right? If I select u value to be secant, what's the derivative of secant? Secant tangent. Is that going to pair up nicely with what remains here? Not quite, right? So let's test the other one here. What if we let the u value be tangent? What's the derivative of tangent x? Secant squared. So that's going to handle things a little bit nicer, right? We see that the puzzle fits a little better if we select the u value being the tangent, because we kind of look ahead and see, okay, looks like that should work out because we want the derivative to pair with what remains in the problem to get those to cancel out, right? We can't do u substitution unless we can see a path where the x's can go away. Okay, so those are our targets. We're hoping that the secant squared goes away, which it should because we kind of predicted it. All right, so our u value is just tangent x. Du over dx equals secant squared. Cross multiply. Okay, solve for dx. And we make our initial set of substitutions, just the ones that I underlined in red. Okay. All right, so what do we have to begin with? Well, u to the 5th, right? Don't forget about that 5. We still need that as part of our problem. I'm going to copy down secant x squared because it hasn't been resolved yet. Dx gets replaced with du over secant squared x. All right. Do the x's go away? Yes. Numerator and denominator, right? Okay. No coefficients to keep track of, which is fine. We just have u to the 5th du. Okay. Much easier problem than when we began, right? That's the whole purpose here. All right, power rule. u to the fifth becomes plus c. Okay. U is only a temporary variable. We want to bring what back? 10x. So we can leave that 6 below, or we can push it out in front. Either way is fine. You can bring this 6 in shorthand form, put it between the n and the x. You can do that either way. Okay. Any of these is fine. Okay. Example 6. What's our first option whenever we see a problem? Power rule. Okay. Can 6 be done with power rule? It can. Okay. I know that so whenever you see parentheses, don't assume that it's a U substitution problem. There's not a whole lot that's preventing us from expanding this, right? So we can't do it. This isn't the same thing as this. Yeah. If there's only one variable in the denominator, we can split up and bring it up. There's no issue. So this is manageable with power rule. Okay. So I want to kind of show you that just because you see parentheses doesn't mean it's a U substitution problem. Always eliminate your power rule option before you step into U substitution. All right, so we can bring that square root of U to the top as U to the -1/2. Well, let's see. Sorry, the way that I'm presenting it is splitting up first, right? Okay. So we bring all the denominators up. There's no need for U substitution. This is not a complicated enough problem where we need U substitution. And if you attempt to do U substitution, you're going to get stuck. Okay, so it's not where, oh, I'll use the complicated method to solve the easier problem. It has to be solved using power rule. It doesn't work with U substitution. Okay, so that's why it's important that we always have to explore our first option. Make sure that is carefully considered before you move into anything else. The first term is ready to go. Here I'm combining the y's together. I have the add exponents. 1 minus 1/2 is 1/2. And now both terms are ready for power rule. Okay, force that 1/2 up to the top. That becomes what? 3 times 2, which is 6. 3/2 in the denominator comes up as 2/3. Okay, we're not going to move on to example 7 and 8. We'll save that for tomorrow, but I want us to do more practice with U substitution problems. So if you can find space elsewhere or on a separate sheets, let's look at some more examples here. Okay, so this is the example that I showed you earlier of the chain rule that ended up being this mess, and we know it's going to bring us back to a simple looking trig problem. So now I think we can handle it a little bit more manageable now that we have the tools. First, we recognize that there's no rule that can handle this mess of a problem. I can't just do integral of sine, integral of cosine. There's the multiplication, right? If it was a plus in between, then that's maybe more feasible, but anytime there's multiplication involved, we can't as easily separate and treat them independently. Okay, they're kind of stuck together. So maybe you're thinking that your u value is 3x, but that's not enough, okay? Because that's not going to handle the fact that the sine and cosine, we need basically one of them to disappear because we don't have a rule that can handle sine and cosine multiplied together. So let's see if we can create another set of parentheses or a bracket. Where else can we create? Yeah, the sine cube can be written as what? Sine 3x cubed. Okay, so this feels a little better. What could be our u value? Sine 3x, right? 3x alone is not large enough because it's not going to take care of one of these trig functions. But that sine of 3x is a lot more significant, which is going to, the bigger your problem is, the larger your u value needs to be to handle all the moving parts. Okay, so those are our targets. Our targets is to replace those, and then we'll keep everything the way it is, and we're hoping that the cosine 3x will go away. Okay. Okay, du dx, sine 3x becomes cosine of u times u prime. Yeah. Cross multiply. Okay, I'm moving that coefficient out in front because I don't want to get these two confused. I don't want to accidentally make this 9x, right? Because this 3 and 3x are in different places. One is inside and one's outside. I think. Let's solve for dx. All right, so I'm just substituting, replacing what I see in red. Make sure that you copy everything back into the problem. We don't want to lose all the parts that we haven't dealt with yet. So 12 times. What's next? 12 u to the third. Okay, write down that cosine. I know we want that cosine to disappear, but we haven't dealt with it yet. dx gets replaced with. Good. All right. Do we see some matching parts here? Cosine 3x, right? That's good. Cosine goes away, and the 3x goes away. All right. What else? Anything else we can reduce? 12 and 3, right? Good. We have two coefficients. We can pull those out or just reduce them first. 12 divided by 3 is 4, so that's a coefficient that's hanging out in front. Okay. Are we looking at an easier problem? Yes, right. So that's always a good test, right? Make sure it's an easier problem. And also, we want to make sure that there's a rule that can handle this, which we can. This is definitely a power rule problem. So now ready for power rule. U to the third becomes u to the fourth over 4 plus c. What goes away? 4 goes away. U is a temporary variable. Replace the u back in terms of sine 3x. So what initially was a difficult process, and we didn't have a u substitution. So having u substitution is nice because it kind of helps us gives that organized way of kind of keeping track of all the parts to bring us back to where we need to be, right? Okay, so we're kind of coming around full circle. We learn how to do chain rule, and now we learn how to go backwards, right? It's a lot more involved there, but okay. All right, so you guys have homework for 4.5a, and we'll explore more involved types of problems on Monday. All right, come get your phones.